I'm away.
Thank you.
I'll let you do. I'll let you start the service one.
Let's start. Thank you. And thank you everybody for attending another LIDNUG event. This month we are going to see Jeffrey Richter from Wintellect doing a lock-free thread synchronization. And before we proceed, I'm just going to apologize for my voice. It may collapse out a little bit. It's not bandwidth issues. It is laryngitis. Quick thank you to our sponsors before we start. I want to say thank you to Thread and to Thread for their continued support. And a big special thank you to Syncfusion for all their support around the LIDNUG and Wintellect events. Some upcoming events that we have Put in the Cloud in Your Pocket, Part 2, John Garland. This is another LIDNUG and Wintellect event on August 23rd. September 14, we have unit testing spring cleaning with Gil Silverfeld. September 18, we have Jeff Precise. This is another LIDNUG and Wintellect event as well, and it's taking a drive with HTML5. Again in October on the 11th, there is .NET Performance Tuning by John Robbins. Also a LIDNUG and Wintellect event, followed by Mitch Harpour's Practical Patterns with JavaScript, MVC4 and HTML5, which is also a LIDNUG and Wintellect event. We're going to finish up with November 15th, building single page apps, SPAs, with John Papa. So a fairly stacked event months coming up, with only October being having one event so far. Quickly, the guys from Wintellect are going to give away a $499 virtual training course. The Wintellect consultants and trainers are some of the best in the industry. Definitely cannot go by with this year. We will announce the winner at the end of the presentation. My suggestion is that if people have signed in only with a first name, that they either sign in with their surname as well, so it's a bit easier to locate them. Also, Syncfusion, who's just released, I should say, Metro Studio 2, a fantastic Windows 8 icon design application. And they've also put together a tech portal, syncfusion.com/tech portal, where there is a host of ebooks from the Succinctly series. One of our favorite group managers from LIDNUG, Peter Shaw, is also going to be releasing a book there. Lastly, some housekeeping for LIDNUG. Our calendar bit.ly, that's LIDNUG_ISS, twitter.com/LIDNUG and facebook.com/LIDNUG, our social avenues. If you have any questions or comments, please send us an email at info@lidnug.org. Keep up to date with all our upcoming events. You can both subscribe to RSS feed and calendars at lidnugevents.eventbrite.com. Before I hand over to Jeffrey, I just want to follow up with an announcement that LIDNUG is also in the progress of creating a Windows 8 application. This application is built by the community and by members of the community and is shaping up quite nicely. Very much looking forward to seeing how this is going to turn out. Now, Jeffrey, thank you very much for coming on board again. I'm going to hand over to you.
Okay. All right, let me see if I can get my slides up here. All right, it looks good, right? You can see that?
Yes.
Okay, excellent. All right, well, good morning. Welcome, everybody. First, I'll tell you that I have made these slides downloadable. If you go to the handouts in the top right, you'll be able to download the lidnug.pptx file. Also, I think there's a way for you to download as a PDF if you would rather have as a PDF instead of PowerPoint. I have a demo that I'm going to do later on which has some code in it, and I'm not making the code downloadable. However, the code is on one of the slides. So if you download the PowerPoint file, you'll be able to just copy the code out of the slide and then paste it if you want to do the experiment yourself that I'll be demonstrating for you a little bit later on. Also, this is very informal, so feel free to put questions in the Q&A manager, and I will look at that periodically as I talk to see if there's any questions to answer. And I'm happy to go off topic and things like that. I'm basically here for about an hour and a half or so to do whatever you would like out of me for that time. On really any subject, but I'm focusing on the threading stuff. But if you want to talk about something else, feel free to do that. Let me do a quick introduction. This is being brought to you by Wintellect and LIDNUG, of course. And Wintellect is a company that we're 11 or 12 years old now. I can't quite remember anymore. And we offer consulting services, training services, design, and debugging services. It was founded by myself, Jeff Richter, and John Robbins. We are the 3 technical partners. And then we have a 4th partner, his name's Lewis, who runs the business on a day-to-day basis. And we do a lot of work for Microsoft. In fact, we're the largest training vendor to Microsoft, but we also do a lot of code development. In fact, one of Microsoft's products, the Expression Web product, was actually written entirely by us. And then Microsoft just puts their name on it, and they document it and test it, but all the software development was actually done by us. And we do a lot of work for other companies as well. So if you have any consulting, training, or design debugging needs, you might want to consider Wintellect for that. I will be the presenter for this talk. My name is Jeff Richter, and I'm one of the owners of Wintellect, but most people know me from the various books and magazine articles that I've written. I guess it's now been about 20 years or so since my first one came out. And I've written about maybe, 15, 16 books, something like that. On this slide here, I show my 2 most recent books that I published. My CLR via C# book, the 3rd edition of which came out about 2 years ago. It was updated last for .NET 4.0 and Visual Studio 2010. And I'm pleased to announce that I am revising that book, even though I vowed I would never write another book. I have revised that book, so the 4th edition will be coming out probably later this year. I've actually done the writing of it, so we're starting the editing cycle now where the editors will review the chapters and send them back to me. So it'll take a couple months for that to happen, and then the 4th edition should come out very close to the end of the year in just a few months. On the bottom right is my Windows via C, C++ book. That used to have different names like Advanced Windows and Programming Applications for Microsoft Windows, and that's the 5th edition of the book right there. And that book was last updated for Windows Vista, and it's a native programming book. That book, I vow that I never really, honestly, will never revise that book again, because going back to native code after having worked in managed code for so many years was such a painful experience for me. Getting all the asterisks and ampersands and arrows all in line and everything was just very, very painful. Plus, it seems that interest in native software development has waned quite a bit. And so I don't intend to revise that book again. There's a chance I would do a Windows runtime book, and there's a possibility that might happen, but I already have a lot of content, but it's hard to say right now if that will happen or not. I also do a lot of consulting work, so I'm actually kind of in the trenches, architecting software and building software. I do a lot of work for Microsoft internally. I live very close. My house is just 3 miles away from Microsoft's main campus, but I do work for other companies too. And then I also provide many ways for people to contact me. So if you would like to be my friend on Facebook, I will befriend anybody who wants to be my friend. If you want to follow me on Google+, if you want to find me on Twitter or on LinkedIn, I'm available on all of those. I also put here on the slide the URL for my blog where I post technical things. I've done a couple of Windows runtime things recently, and I also did some Windows Azure stuff recently. And then at the bottom is my email address, where certainly you can feel free to email me. Please don't send code that says, can you help me find the bug in this? Our consulting service is best for that. But if you just have a question about something that I talked about today in threading or anything that I discuss in my books or something like that, I always make myself available by way of email. So feel free to contact me. We have a couple of Wintellect events that are coming up. We have some webinars that are usually a couple days in duration and virtual courses, and we have some other events too. And you can learn more about those events by going to this link here, the bit.ly/Wintellect Events website. Wintellect, we also have our conference that we do usually once or twice a year, and it's called the DevScovery Conference, and this year it is on October 1st through 3rd in Houston, Texas. And I'll be there doing many presentations, and so will Jeff Procyse and John Robbins. We have 3 tracks that all run concurrently over this 3-day period of time. And there's plenty of time to have one-on-one discussions with us and meet with us and talk about things that might be affecting your work. We really make ourselves available the whole time for whatever it is you would like to use us for. And below is the link for more information on that. And if you register now, you'll receive a $100 discount to that conference. So we hope to see you there. We also have a couple of partner offers here. Thank you for registering. And as was already mentioned, we're giving away this $499 value for a virtual training course, but you have to be present at the end of this session to win that. And then there's some stuff here about Sync Fusion as well, which was also mentioned earlier too. All right, and so now without any further ado, we'll start focusing on the actual topic of today, which is thread synchronization and the mindset. And again, feel free to put questions in the question manager as I go on, and I'll stop periodically to answer those. So let's first talk about the mindset of thread synchronization and what really is synchronization all about. The purpose of thread synchronization is that it prevents corruption of state or data when 2 or more threads could access that shared data at the same time. And you'll notice on the slide here, I emphasize at the same time, because it's really all about timing. Thread synchronization is all about timing. If I have a piece of data that can be touched, by some thread now, and then another thread could touch that data, but I know that thread can't touch it at the same time, can only touch it later, then thread synchronization isn't required. It's only required when it can happen at the same time. And because it's all about timing, we don't have tools available for us today to analyze our code for timing. A lot of times people ask me, can't the C# compiler analyze my code to see if I need to add thread synchronization, or couldn't the common language runtime just automatically insert thread synchronization code over some data structure for me? And the answer is no, none of that is possible, because the compiler compiles your code and it's not even running yet. So timing only occurs at runtime. It doesn't occur statically at compilation time. This is a dynamic thing that is happening at runtime. And while the common language runtime is present while your code is actually running, the JIT compiler that's compiling the code, and it would be responsible for inserting the thread synchronization, when it compiles the code, it is compiling it for the thread that's currently calling that method. The common language runtime doesn't know about other threads that are doing other things. And so the CLR also doesn't have enough knowledge to be able to do this. So the only way to make this work is that you, the software developer, you have to imagine in your head if there is a piece of data that could be touched by 2 or more threads simultaneously, then the onus is on you to make sure you've inserted the source code to make sure you do the thread synchronization correctly. Oh, let me just, you can't see that. Good. So this makes thread synchronization very error-prone. A thread must voluntarily request permission to access the data. And by voluntarily, I mean that the onus is on you. No one's holding a gun to your head saying to you, and don't forget to enter a lock before you enter this piece of code, then release the lock when you're done. And if you have 10 places in your code where multiple threads could access a shared resource at the same time, and in 9 of those places, you do the absolute right thing, where you create a lock, and then you enter it, you execute the code, or you touch the data, I should say, and then you release the lock. But then in one place in your code, you forget to do that, then the resource is toast, and it can become corrupted. And of course, the real problem here is you generally won't see that happen, because it only happens if the timing is just bad, so that the one thread that you is executing the code you didn't put a lock around. If it happens to hit that at the same time, another thread is hitting the data which you did put a lock around. And on most computers today, it's unlikely that applications are designed so that multiple threads are hitting the same data at the same time. So it's unlikely that your testing is going to show this. So very error-prone thing, very hard to get it right. The next thing to notice about thread synchronization is that it comes with really bad performance characteristics. A lot of people that I talk to don't ever seem to really think about this at all. Let me walk you through an example. At the bottom here, I have this LinkList class. And the LinkList class has a private field in it called m_head, which is of type node. Now, this field here refers to the node or head of the linked list. Then I have an add method here, which you can call in order to add a new node to the linked list, and you simply pass in the new node as an argument. Well, in order to add a new node to the linked list, it's a fairly trivial and straightforward thing to do. What you do is you take the new node that's being passed in, and you set its next field to point to the current head, and then you make the current head refer to the new node that was just passed in. And now we have inserted a new node at the head of the linked list by doing these two reference assignments here. These two reference assignments can be done by any CPU today phenomenally quickly. I mean, it's just moving to 4-byte or 8-byte values, depending on 32-bit or 64-bit machine, from one place to another place. So that's very, very quick. But now as you write this code, you might say to yourself, wait a minute, what if two threads call this add method simultaneously? If two or more threads call this method simultaneously, then these two assignments might not be performed as a single atomic unit. And it's possible that one thread could set its node next to the head, and then the other thread could set its new node next to the head, and now you have corrupted the linked list. So then you say to yourself, well, I don't want that to happen. So in order to ensure that these two assignments get performed as a single atomic operation, I need to make sure that only one thread can execute this code at a time. So in order to accomplish that, you would normally new up some kind of lock inside your class, and then you would acquire that lock, then execute the operation you want to perform as an atomic unit, and then you would release the lock when you're all done. And now you have made this add method thread safe. And that's great, because now if multiple threads call this method at the same time, the linked list will never become corrupt, and each node will be added one in turn. But what a lot of people don't realize is that you have also hurt the performance of this method pretty significantly. These two reference assignments, which the CPU can execute very, very fast, while you've now probably made this method an order of magnitude slower by calling acquire and release in it. You see, these two threads, or more threads, could be executing on different CPUs on the machine simultaneously. And if that happens, when these two different CPUs call acquire at the same exact moment in time, the CPUs, they have to talk to each other. And they have to communicate so that one CPU is the winner and the other CPUs, plural, are all the losers. And this communication of having the CPUs communicate with each other can add a pretty significant performance hit to this application. Number one. Number two, because only one thread will be elected as the winner and will be allowed to return from acquire to execute these two statements here, all the other threads that are the losers, those threads are generally put to sleep, so they're not allowed to execute code anymore. So now the performance hit of those other threads actually approaches infinity. And especially if release is never called. If release is never called, like maybe an exception gets thrown in here, like a null reference exception is possible, then release would never get called, and now those other threads would all be deadlocked and would never make any further progress. So the performance gets phenomenally slow in that case because the other threads just completely stop running. And then another thing that people don't fully appreciate is the increased overhead. I highly recommend that people use the thread pool. The thread pool is a very efficient way of consuming and using threads inside your application. The thread pool creates a small number of threads, and then you queue up tasks to the thread pool, and then those thread pool tasks get rented, if you will, to go and process a task, and then the thread comes back to the tool to go and process another task, and so on. And this means that you have very few threads in your application, but processing a massive workload. And that's a very efficient way of using resources to write an application. But there's a problem with this. And the problem is that when a thread pool thread is blocked for some reason, like if a thread pool thread calls this add method, which internally calls acquire, and acquire blocks that thread pool thread, then because that thread pool thread stops running, the common language runtime's thread pool code goes and creates a new thread to replace the one that has stopped running in order to keep all the CPUs on the machine busy and saturated with doing actual work. So creating a thread in Windows is very expensive. Creating a thread means the allocation of a megabyte of memory for the user mode stack. There's also another 12K or 24K for the kernel mode stack. There's a thread environment block that has to be created. There's a kernel object that Windows has to create for the thread. There's a lot of data structures that have to be allocated and all initialized, which takes time. And all this happens when a thread fails to acquire a lock that it wants. So now the performance hit of putting thread synchronization into this add method here starts to skyrocket in your application. And lots of memory starts to get allocated, performance starts to deteriorate. So there's a lot of the problems here that are associated with thread synchronization and the mindset. So what should you do? What you should do is you should avoid shared data as much as possible. Shared data such as static fields. When you have a static field, all threads can go and access that static field. And so you might need to protect it with thread synchronization. Another thing to really think carefully about is shared heap objects. When a thread calls new to new up an object in the heap, the new operator returns a reference to that object. At that moment in time, only that thread has access to that object. No other thread can see it, and therefore no thread synchronization is required. On the other hand, if that thread now takes the reference it got back from new and then hands it off to another thread, maybe by publishing it into a static field or maybe by calling something like thread pool queue user work item and passing the reference as the object state parameter to that, then you're handing a reference to this object off to another thread. Well, if you do that, now we do have multiple threads that could touch that object on the heap, and now there is the potential for that to happen simultaneously, and now you would start to need to consider, do I need to synchronize access to that so that it doesn't become corrupted? So the best thing for you to do is to use unshared heap objects. That is, have a thread call new to create an object on the heap and then hold on to that reference. Don't give that reference to that object to any other thread in the system. Just have that one thread hold on to it. Or if that thread wants to give it to another thread in the system, that's okay, but then the thread that created it should no longer use the reference anymore. It should stop using it, and then the other thread now would have exclusive access to that object, and therefore no thread synchronization is required. Also consider using value types. Value types are copied around the system whenever you pass them around. So if I have an integer or a date time that's being used by one thread and I pass that over to another thread, the other thread gets its own instance of that. And so no thread synchronization is required. Now, of course, this may not give you the semantics you desire in your application, so you have to think that through. But if it's possible, go ahead and do this. You might also want to consider string, right? Everybody knows that strings are immutable. Strings are reference types. They're not value types. But because they're immutable, they have value type semantics. That is, you can pass a reference to a string to 10 threads that are all accessing the string simultaneously. But because strings are immutable, no thread synchronization is required on the string, because after it's been created, it can never have its state changed. So you might want to consider defining your own classes, reference types, that have this same kind of immutability aspect to them. That once you've created it and initialized it, make sure that you don't provide any methods or properties on it that could change the state. Then you can hand references to it to other threads, and you don't have to worry about thread synchronization. Also, as I mentioned here on the slide, shared read-only state is okay. So certainly, if you have state that's read-only, which again, string is an example of that, or if you create your own classes that once created become immutable, then they're only being read from that point forward, and no thread synchronization is required for read-only state. Okay, so that's that first slide with the mindset. I do see there's one question, so let's see what we got. Feel free to post more. How is the thread synchronization happens in the cloud environment Azure where multi-tenant is the scenario? Well, again, the onus is on you. I've actually done a lot of work with Windows Azure, and what I'm focusing on really in this slide deck is how to scale up, which is how to have a bunch of code running on a single machine that has shared state. With Windows Azure, that's more of a scale-out scenario, where the single machine, you fine-tune the code as much as you possibly can so that that machine can handle as much load as possible. But maybe you have so much load coming into that machine that just the physical resources of the machine, like the CPU speed, the amount of RAM you have, the amount of hard disk space you have, and so on, network bandwidth, simply cannot handle the load. In that case, you need to scale out and use multiple machines. That's what Windows Azure and cloud environments are really for, is for the scale-out scenario. In that case, you don't have shared state on a single machine anymore. In that case, you take your state and you move it to a different repository, like a SQL database, or if you're using Windows Azure, you can use Windows Azure Blob Storage or Windows Azure Table Storage as a central repository, and then all the different machines go and access that state on those different machines. In that case, because they're on different machines, synchronizing access to that state has to be done in a very different way. You can do things like take leases on it. For example, Azure Blobs have a lease mechanism where one machine can say, I want to take a lease on the blob, and then no other machines can write to that blob while that lease is held. And then you would release the lease when you're done. So that's one thing that you can do. Another thing that's typically done in cloud environments is an optimistic concurrency pattern, where you, let's say, read an entity from a table, and each entity has an E tag on it, an entity tag on it. In Windows Azure Tables, they use a timestamp for that, a date timestamp for that. And then you read that value, you make changes to it, and then when you write it back to the database, you say, well, this is the new state, and it should only be taken if no other thread has modified this while I was modifying it myself. So in cloud environments, you'll either use kind of a leasing thing, which is very similar to taking a lock and releasing a lock, or you would use optimistic concurrency scenarios where you don't want to hold a lock because locks hurt scalability so much, as I was just talking about on the previous slide. Let's see, there's another question here. How does the volatile keyword work in C#? Does it implement thread synchronization internally? Well, actually, that's what the next slides that I'll be getting into. So I'll be going into the volatile field access very, very shortly, and I'll be answering that and showing some demos on that in just a moment. How big is the impact on the performance if we use semaphores? How data access? I think you mean just if you use semaphores for data access. Semaphores are horrible for performance characteristics. The kernel objects, anything that is where Windows is involved in the thread synchronization, has awful performance characteristics. So specifically, that would be Windows mutexes, Windows semaphores, and Windows events, auto reset events, as well as manual reset events. In the .NET framework, there are classes, the mutex class, the semaphore class, and the event wait handle class, which has two derived classes off it, auto reset event, manual reset event. Those classes in .NET are very simply object-oriented wrappers around the Windows functionality. And the performance of those is always terrible. So they should be avoided as much as possible if you're trying to write really high-performing code. You're much better off using things like reader-writer locks or using monitor enter and monitor exit. Because they use kernel objects, but they only use them if there's contention on a resource. When there's no contention on a resource, then they don't use those kernel objects. And usually in an application, there's not contention for a single resource because it's very unlikely that two or more threads do try to touch the same object at the same moment in time. In most applications, that is phenomenally rare. And so usually, when you try to access a resource, there's no contention, and the monitor enter and monitor exit, and the reader-writer lock slim class in .NET, when there's no contention, they run very fast. The semaphore mutex and event, they run always very slow, whether there's contention or not. If you go to the DevScovery conference later this year in October in Houston, I'll be doing a whole two-day thing on threading and thread synchronization and scalability, and I go into all of this stuff in much greater detail than what I'm able to do in this hour-and-a-half presentation now. I have lots I could say about all of this stuff, and that I think is very interesting and very important for people who are really trying to build scalable software or just responsive client-side software too. Okay, so let's begin talking about what's known as the CLR's memory model and more specifically volatile field access. Here I show you a piece of code, and this is the demo that I want to perform for you as well. So let's walk through what this code does, or rather I should say, let's walk through what the intention of the code is, and then we're going to see what actually happens. Here, this is a console app. It's a very simple console app, and here's my main method where my primary thread would start executing the code. Inside here, I'd simply display on the console, we're in the main method, and we're letting the worker run for 5 seconds. Then what I do is I new up a thread, and that new thread is going to call this method worker, which I show down here below. After I create this thread object, I then call start on it over here, which now tells the Windows operating system to create a thread, which means it's going to allocate the megabyte of memory for the user mode stack, and it's going to allocate memory for the kernel mode stack, and all the stuff I talked about before. And now this thread is going to start calling the worker method down below. Now, we'll talk about what worker does in just a moment. Let's stay inside main for right now. So after we start that worker thread, the main thread is going to call thread sleep 5000, which says to Windows, hey Windows, don't let the primary thread execute for 5 seconds. So Windows will now take the primary thread off of the CPU and will not allow it to run for 5 more seconds of time. So now the secondary thread is running for 5 seconds. After 5 seconds has expired, the primary thread will return from its call to sleep, and then it will set this variable stop worker to the number 1. Okay. Stop worker, you'll notice, is a field, a static field declared up above. Because it's a static field, it is accessible by all these threads. And it's simply an int32, which I initialized to 0. Now, really, I want you to think of it as a Boolean, where 0 means false and 1 means true. So I had initialized it to false, and then after 5 seconds goes by, I go and set it to true. Then I call console write line to say the main method is now waiting for the worker thread to stop. And then I call thread.join here, which stops the primary thread, and Windows will wake the primary thread up after the secondary thread has terminated. All right, now let's focus on the secondary thread. The secondary thread is executing this method here called worker. Inside worker, I simply declare a local variable x, and I set it to 0. Now, this is a local variable inside a method, so x is always thread safe. Right? Local variables are always thread safe while they're inside a method. And then what I do is I have a while loop, and the while loop keeps adding 1 to x over and over and over again until, or I guess I should say, while stop worker is false. So while we don't want to stop the worker, let's keep adding 1 to the number x. But then in the primary thread, when we set stop worker to 1, which happens 5 seconds after we start the worker, then the while loop should exit, and then this will display on the console window, the worker thread is stopping, and x reached this value. So basically what the worker does is it sees how high it can count within a 5-second period of time. That's kind of the intention. Then the secondary thread will exit from worker, That will cause join to return for the primary thread, and then the primary thread will exit main, which will cause the entire process to terminate. Okay? So what this does is it creates a secondary thread. It lets that secondary thread count or increment x by 1 over and over again for a 5-second period of time. Then we tell the secondary thread to stop running. The secondary thread will then show us how high it counted up into a 5-second period of time, and then the entire process will terminate. Okay, that's the intention of the method. So now, I want to compile this and run it for you. To do that, I'm going to share my desktop now. And over here in Notepad, now let me say, earlier today we were testing the desktop sharing, and the performance of it was very slow. So I've shared my desktop, but I don't know if you can see yet what it's sharing. So I'm going to talk slow, and maybe some of the people I can hear can tell me if everything's working okay.
Nothing there yet. It's starting to run
Really?
slowly.
Nothing yet? Wow, that's really bad. Well, what you will see very shortly is a Notepad window, and in Notepad, I have the same exact code that I showed you on the slide. So if you can see what's on the slide, then you're basically seeing what I'm showing in Notepad. But what I'm going to do is I'm going to compile that code, and I'm going to run it for you so you can see the result. So I'm also going to open up a console window here, and I'm going to move it off to the side, and then I'm going to compile the code. So how are we doing? Can you see the Notepad in the console window yet?
Yes, yes, we can see Volatile.cs.
Okay, great. And in the console window, you'll notice that when I compiled it, I did get a couple of warnings. That's because this is an x64 console window, but if you look over at the top of the Notepad window, this is the command line that I'm using to compile the code, and I said I want to compile it for x86 platform. So I'm compiling it as a 32-bit executable, but in a 64-bit command prompt window, which is why I'm getting these warnings. But the warnings are just warnings. They're not errors. And so I actually did compile the code. You'll also notice that I have compiled the code with the /O switch. So that means I'm compiling it with optimizations turned on. So here's what I'm going to do now. In the console window, I'm going to run the volatile.exe, which was just created. And then I'm going to hit enter. And it says here, main, letting the worker run for 5 seconds. Then 5 seconds has now expired. And it says main, waiting for the worker to stop. And now we're waiting for the worker to stop. But I don't know if you can see this yet or not, but what's happening is the worker is not stopping. And my process is not terminating, and it's never displaying the value of X. My program, the secondary thread more specifically, is actually in an infinite loop, and it has deadlocked my primary thread from ever returning from join. So are you able to see now where it says main waiting for worker to stop?
No, we are seeing still the, oh, now we are.
Now you are? Okay, great. So it's been way more than 5 seconds, let me assure you. Right? And the program is hung. So we wrote that code with good intentions, but it is not working correctly. And in fact, we have an infinite loop, and my application will never terminate at this point. Now what I'll do is I'll force the termination of the application by hitting Control-C in the console window, and that will forcibly terminate the app. But the program is not working correctly. So what is going wrong here? Let's take a look at the code. So I'm going to go back to the slides now, and hopefully that will give you a good experience. Okay. What happened is the JIT compiler, when it compiles this while loop, are you all seeing the code now in my red dot?
Yeah, we are indeed.
Yeah. Okay, good. So when the JIT compiler compiles this while loop, the JIT compiler is an optimizing compiler. And when it looks at that code, it says, hey, inside this method, because the optimizer only ever looks at a single thread at a time. It doesn't care about multi-threaded scenarios. Because again, threads is a runtime thing, but compilation is really a static time thing. So the JIT compiler, it looks at this line of code and says, well, inside this method, stop worker never changes. Inside the worker method, I only ever read from this value. It never gets modified. And so the jitter says, I can actually make this code faster. Let me go and hoist this test outside or before the while loop. And if this is 0, then I'll make this a while true loop. So every time it iterates around the loop, it will never be testing this variable, which means the code will be smaller and the loop will run faster. And that's exactly what happened, is that because stop worker was set to 0, it checked it before the loop, and then when it got into the loop, it made it a while true loop, which turned it into an infinite loop. So the loop was running very, very fast, but it stopped checking this variable, which caused the program to fail to work as we intended it to. By the way, if somehow 5 seconds expired before we got to the while loop, then stop worker would be 1. And in that case, the JIT compiler said, well, if stop worker is 1, jump over the loop entirely and then display the value 0 for x all the time. So the way this code is written, it is legal for the jitter to produce the code in such a way that we will either get 0 or an infinite loop. We'll never get the desired behavior of actually counting up to 5 within 5 seconds. And of course, this is not what we want to have happen. Now, by the way, I compiled this for the x86 platform with optimizations on. If you compile the same code with optimizations off, then the jitter does not perform the hoisting optimization, and it does check this variable inside the loop every time it iterates around. And this means the program would work as we intend. However, this is very discomforting because usually your debug builds are without optimizations turned on, and your release builds are with optimizations turned on. So this means the program would behave the way you intend in a debug build and would fail to work correctly in a release build. And that's usually not what you want. So you have to make sure that you test release builds of your application, especially multi-threaded applications. But the compiler generates, the C# compiler and the JIT compiler, they generate different code for you with optimizations on or off, and you really should be testing your applications with both to make sure that your program is really truly behaving the way you intend it to before you deploy it anywhere. Also, I'll mention that if I change this platform to x64, then the jitter does not do this optimization. Also, if you ARM CPUs are supported now with Windows 8. So if you change the platform to ARM, well, actually, I haven't tested it, so I don't know what happens in ARM. Actually, my guess is, though, that in ARM, you would see exactly what I demonstrated here, which is an infinite loop, because ARM is more aggressive in terms of its optimizations. The x64 JIT compiler is not as aggressive in its optimizations today. But in future versions of the x64 compiler, you should expect that this hoisting optimization would occur, and so you would end up with an infinite loop. So this, what I'm trying to say with this discussion is that different CPU architectures will also yield different results. So if you compile for x64 with optimizations, you would not get an infinite loop today in .NET 4 and in .NET 4.5, but in future versions you might. So you should just be aware of that, okay? Technically, this code is wrong, and the code needs to be fixed. And that's what we're going to get into now, is how do we go about fixing this code. But before I show you how to fix the code, let me show you another example of code that experiences the same kind of problem. In this code here, I have a class called out of program order. The name of the class doesn't matter. But what is important is that the class has two fields in it, a flag class, a field, and a value field, both of which are 32-bit integers and both of which are initialized to 0. Now let's imagine that I have a thread that executes this thread1 method, and I have another thread, a different thread, that's executing the thread2 method. Well, let's look at thread1. In the thread1 method, this says, let's put a 5 in value, and let's put a 1 in flag. Now, this method could execute first. Remember, thread is all about timing. So we have to run through in our head different timing situations or scenarios. So let's say this thread1 method executes first. And then another thread goes and executes thread2 second. Well, in that case, Thread 2 will see that m underbar flag is 1, and therefore it will display the value of m value, which means 0 would be, or I'm sorry, 5 would be displayed on the console window. Of course, it's also possible that thread 2 could actually execute first. And if it does, then m underbar flag would be 0, so the if statement would be false, and therefore nothing would be displayed on the console window at all. But you have to look at other timings too. What if thread 1 sets m underbar value to 5, and then it gets preempted before it puts a 1 in flag? So it runs partially before thread 2 starts executing. Well, then in thread 2, m flag would still be 0, and nothing would be displayed. It's also possible that thread 2 could start executing first. Then it could check if m flag is equal to 1. It's not, because it would have been 0 up above, over here. And then it gets preempted. Then thread 1 could run all the way to completion. And then thread 2 could continue its execution. But because flag was 1, or flag it saw 0, it would not call display. So it looks like, when we run through these with different timing scenarios, it looks like either nothing would be displayed or 5 would be displayed, and they're the only two possible outcomes. Well, if that's what you did, you would be wrong. As I mentioned here in this comment, this code could actually also display the number 0 on the console window. Now here's how. When the compiler generates the code for the thread 1 method, thread 1, the intention here is that thread 1 puts a 5 into value and a 1 into flag. That's the intention. But what's really implicit here is the order in which those things are done is unimportant. You see, when a function calls thread 1, when that function thread 1 returns, there's a 5 in value and there's a 1 in flag. We know that. But we don't know, nor should you care, in what order those things were done. And it is possible that the compilers and the CPUs could optimize your code in such a way so as to alter the order of these statements. And if that happens, then it is possible that a 1 could be put into flag first. Then that thread 1 could be preempted. Then thread 2 runs, and it sees that there is a 1 in flag now. And then when it sees what's in value, it sees the 0 because the 5 hasn't been put into value yet. And therefore, a 0 would be displayed on the console over here. So this is all very possible. And the only time you would ever see something crazy happen is if the timing of it was just wrong. If the timing of it, is normally everything's working fine, then yes, you're only ever going to see a 5 or nothing. You would never see 0 displayed. But if the timing is just wrong, then you could see 0 displayed. So technically speaking, this code that I'm showing you on this slide is also wrong. It has a bug in it. And this is the same bug as what I showed in the other example a moment ago. And we need to fix both of them. So now, how do we fix them? Well, the way we fix them is we use special methods that are inside the framework class library. In the system.thread class, there are these methods called volatile write and volatile read. And these special methods, they are special methods. You could not write methods that do what these methods do. These methods are looked at specifically by the compilers and by the JIT compiler. And when the JIT compiler sees calls to these methods, the JIT compiler produces special CPU instructions. So rather than when the jitter sees calls to these methods, rather than the jitter producing CPU instructions to call a method, the jitter instead inlines those methods and produces special CPU instructions. And those special CPU instructions are understood by the CPU that you're running on, the x86, the x64, or the ARM CPUs that you're running on. And those special CPU instructions tell the CPUs to do special things. In particular, at a high level, what these special methods do is they turn off some CPU optimizations. Okay, that's the high level, what they do at a high level. How do they do that? Well, first they tell the CPU that data cannot be cached in a register or in a temporary variable. A lot of times compilers, when they are compiling your code, the C# compiler, the JIT compiler, they can introduce temporary variables into your code in order to improve performance. But when you use volatile write or volatile read, that tells the compilers they cannot introduce temporary variables to cache the value of some other variable that you have in your code. Furthermore, when you call volatile write, it tells the compilers in the CPU that any earlier program order loads and stores must occur before the volatile write. And volatile read tells the compilers in the CPU that any later program order loads and stores must occur after the call to volatile read. Now, when I was first learning this stuff many years ago myself, I found this all to be phenomenally confusing. And so I've come up with a simple summary. And if you just remember the simple summary, you will be good to go and you'll be doing the right thing. And the simple summary goes like this. When threads communicate using shared memory, write the last byte using a volatile write and read the first byte using a volatile read. And if you remember to do that, then you will be good to go. So let's go to the next slide, and I will show you now how to fix the code. Well, if you go back to the summary, when threads are communicating using shared memory, well, my thread1 method uses flag and value. That's two pieces of memory. And then thread2, it also uses flag and it uses value. So that's two other pieces of, that's the two same pieces of shared memory. So I have two pieces of memory that is shared. But we go back to the summary. Write the last one using a volatile write. Well, in the thread1 method, two writes were occurring. I was writing a 5 into value, and I was writing a 1 into flag. Well, the last write has to be done using thread.volatile write. So the first write is a normal write, a non-volatile write, if you will. And then the writing of a 1 into flag is now being done as a volatile write. Let's look at the thread2 method. Well, in this method, I read flag and I read value. But if you go back to the summary, the first read should be done volatile. Well, the first read is mflag. So I now read it using thread.volatile read. And now the second read is a normal or non-volatile read, if you will. And now because I've done this, I will either get nothing displayed or I will get 5 displayed on the console window. It is now impossible to get a 0 displayed on the window. Now, what's actually happening here? What's actually happening here is this call to volatile write says to the compilers and the CPU, you can only put a 1 into flag after a 5 has been put into a value. So we've now, by calling volatile write, we have enforced ordering of these instructions, of these statements. A 1 can be put into flag only after a 5 has been put into value. And if we look down below, this says M under value can only be read after M under bar flag has been read. You see, I said a moment ago, the CPU can sometimes read something and cache it into a temporary variable, and that could have happened earlier, in which case it could have read value and cached the 0 into a temporary, and then a code called display passing in the temporary. But because of the volatile read call, it's not allowed to cache. Well, it can't cache flag into a temporary, but it also says that value can only be read after the call to volatile read. So this means that value could be cached into a temporary, but that reading must occur after the volatile read call. So this fixes that code and makes it work correctly. And then in my previous example over here, in this one, what I would do is I would make this assignment here a volatile write, and then over here in the while loop, I would put in here a call to volatile read. And by putting the call to volatile read in the while test, that says to the compiler, you cannot hoist this out anymore. The reading of this variable must occur with every iteration of the loop. And that's how we go and fix this and get rid of the infinite loop to make sure it works correctly all the time. Okay, I see there's a question, so let me see what the question is. What if there are more than 2 writes and a read? That's a good question. So let me go back to the previous slide here. So if I had, let's say, value 1 and value 2 and value 3, and I want to set them to, 3, 4, and 5 respectively, then I set 1 into flag. Well, the assignments to value 1, value 2, and value 3, those assignments can be done in any order. But all 3 of them must be complete before the 1 goes into flag. Okay, so the lines above, the non-volatile, those can be optimized and reordered in any way the compilers and the CPU sees fit. The only thing is that they must all be done, though, before the 1 is put into flag. Similarly, in the read down here, I could read M value 1, M value 2, and M value 3, and the compiler can optimize that code down below in any order that it wants. But they can only optimize that code that is below the call to volatile read. Right? So that's what's happening there. Are there any other questions anyone wants to ask? Can we use memory barrier attribute to avoid this problem? I am not familiar with a memory barrier attribute. There is a memory barrier method that's on the system thread, threading.thread class. And you can use memory barrier, yes, but it doesn't perform as well. So volatile read and volatile write give you better performance, and actually the code is more naturally written with volatile read and volatile write. So that's why I don't even mention memory barrier here. And again, I'm not aware of a memory barrier attribute. Oh, there's several more attributes here. Is there an attribute you can apply to a method to turn off optimizations? Actually, I believe there is. I believe there's a method impl attribute, and you can pass in there a method impl, turn off optimizations. But even if you do that, it's really a hint to the jitter. I don't know if it's guaranteed, and you certainly would not want to put this attribute on every single method in your code. And even if you compile your code without optimizations turned on, then it's still no real guarantee that this is going to work. I mean, really, you need to fix the code. It's the only way you're going to have guaranteed that the code is going to work the way you want it to work. You really should fix the code. If M underbar value is set to 10 in thread 2 after the volatile read of M underbar flag, could we display 5 instead of 10? Yes. That is, and if this is also after the volatile write, I assume, right? So you're setting M underbar value to 10 after the volatile write up above in thread 1. You don't mention that part, but I think that's what you mean. Then could you see the 10 instead of the 5? Yes, then you could see the 10 instead of the 5. What if nothing gets displayed in method 2? What is nothing gets displayed? Nothing means that if we read flag and we see 0, because that's what it was initialized to, so maybe this thread executes first before this thread runs at all, then this would come back with 0, so this would be false, in which case nothing would be displayed, because we wouldn't call display over here. That's what I meant by that. Oh, it looks like there's... Okay, so I think I've hit all the questions that are in here now. All right, so 9. So let's move on. Now, in order to simplify your code, so some people are talking about an attribute, or, I mentioned maybe compiling with optimizations off, and those things exist, but they do not guarantee you that the code would still be correct. So if you really want to simplify your code and guarantee that the code works correctly and it is correct, C# offers a volatile keyword which you can apply to fields. And here what I'm doing is I'm taking the pivot field, if you will, right? So the field that was using as the pivot variable between these two different methods, which was M underbar flag, I've now marked the field itself as being volatile. And when you do that, And here I'm saying M flag equal 1, but this is, because flag is a volatile field, this is the same thing as what I showed on the previous slide. That is, it is the same thing as saying thread.volatile right M underbar flag equal 1. And in the if statement down below over here, this is the same thing as saying thread.volatile read M underbar flag. So it's just simplifying the code here, but it's doing the same exact thing as I showed you on the previous slide. However, I don't like this at all. And I would strongly discourage you from using the volatile keyword. And the reason is because when somebody's looking at this line of code, M underbar flag equal 1, that does not look like it's a volatile right. And somebody who's looking at this code might say, you know what, let me change the order of these lines. They might cut and paste, to reorder these lines of code. And when they do that, they broke the thread synchronization here. And so I prefer the previous slide with the call, the explicit call to volatile write and the explicit call to volatile read, because these are huge red flags to somebody who's editing these methods that say to them, hey, if you are modifying the code in here, be very careful, because there's clearly some thread synchronization thing that's going over here. Do not put M underbar value after the call to the assignment of 1 into flag, because if you do that, you might be breaking thread synchronization. So I like calling thread volatile read and thread volatile write explicitly in my code, because they are enormous red flags that really tell people who are editing this code, or myself, sometime in the future, I got to be really cautious when working in this code over here, where I could break thread synchronization. And again, you would only find out if it's broken if the timing was just wrong during your testing, which is very unlikely to happen for most people. Let's see, another question has shown up, so let's go and answer that. Why not make both members volatile so that the order does not matter? Well, wait a minute. So first of all, yes, you could make both fields volatile, but the order would still matter, okay? So if you set flag equal to 1 first, then this could see flag 1, and then this would display as 0, because this value hasn't changed, right? So the order that you write the code is important, and volatile doesn't completely say, compiler, just figure out the right thing to do. Right? What volatile says is, compiler, the order in which you wrote the code must be maintained. Right? But you must still write the code in the correct order. But the reason why you don't need, well, first, you don't want to have too many things being volatile, because volatile does hurt optimizations. And the more things you make volatile, the less optimizations the system can do for you. And we like it when the compilers and the CPU optimize code. We like that a lot, actually. And so we want to leverage that. I mean, alternatively, if we didn't care about that, then the compilers themselves could have just assumed everything was volatile. And then we wouldn't have to worry about this volatile stuff at all, but our performance of our applications and our memory size that it would need would increase dramatically and would just be horrible. Right? We, as software developers, we want to think in these high-level languages like C#, and we want to think in terms of abstract concepts like methods and virtual methods and interfaces and delegates and callbacks and things like that. We find these concepts, these abstract concepts, to be very useful for us on a day-to-day basis when writing code. But ultimately, our compilers have to convert these high-level concepts that we want to think in as human beings into intermediate language instructions or CPU instructions that the CPU can process. Right? The CPU doesn't know what a virtual method is. CPU doesn't know what an exception is. CPU doesn't know what a delegate is or an interface is. And so the compiler has to translate from these high-level abstract concepts into CPU instructions that ultimately have to be produced. And it could make all the variables volatile to do that, but in doing so, it can optimize our code and can do a good conversion for us here. So we like these things. We don't want everything to be volatile. let's look at the next question here. In your good code example, if someone reorders the variable declarations, would that break the code? You keep saying order matters, order of declaration lines. So let me go back. The order of the assignments here, if I set, all right, let's look at this version, just because I think it's easier to look at. Right, so if I change the order of these, then if I put a 1 into flag first, then in thread 2, we would see a 1. And then either we will see 0 or we will see a 5 over here, depending on whether we get preempted up above. But I want to make sure that a 0 never gets displayed. Right, so my goal is I either want 5 displayed or nothing displayed. Right, I either want this code to execute if this has executed first, or I don't want this code to execute at all if this did not execute first. Right, that's really my goal. And I'm saying that I want this code to execute, and then I want it to show basically the results of what happened if this thing executed in its entirety first. And so the order here, 5 is the result, and 1 in flag is saying I have computed the result. And so this says, if you have computed the result, let me see what it is. Right? And if you haven't computed the result yet, then I don't want to show you anything. Right? You can kind of think of it logically as this is what I'm trying to do. If I reorder the assignments in thread 1, then I'm saying I have computed the results, but the result would then be 0, and then later in time, I would be changing the result to 5. So this, depending on a race condition and on timing, would either show the 0 or would show the 5, and that's not giving me the behavior I desire. I hope I'm making this clear. I know this stuff's very confusing. I mean, we as human beings, we're not used to thinking, what happens if this happens and then that happens at the same time, and this happens like first and then this happens a fraction of a second later, or this thing happens. Very confusing to do that. I've been thinking and working with threading and thread synchronization and race conditions for 20 years of my life, almost every day of it, including weekends. And so, after 20 years of seeing these patterns and working with this kind of stuff, it feels very natural to me. And I'm hoping that I'm able to get that across to you, in basically an hour and a half conversation. If it's not working for you, I'm happy to stay online and take more questions. Why is the volatile keyword not allowed in C# on in64? Good question. The reason is because in order for volatile to work, the field has to be properly aligned. That is, a 16-bit value must be on a 16-bit boundary, and a 4-byte value must be on a 4-byte boundary, and an 8-byte value must be on an 8-byte boundary. And an in64 is an 8-byte variable. But by default on 32-bit systems, a in64 can be aligned on a 4-byte boundary, does not have to be aligned on a 8-byte boundary. And because that could happen, the C# compiler says, I can't guarantee you that volatile will work correctly if this thing is aligned improperly. And C#, the language, doesn't give you easy ways of controlling alignment. And so that's why they forbid it. They say this is a compiler error because we can't guarantee you it will always work. That's why. What if we need to manipulate fields in a class object atomically? If you need to manipulate multiple fields in an atomic way, then you have to use what I showed on the first slide, which is you have to create a lock, and then you have to enter the lock, then manipulate all the fields, and then release the lock, just like I did in the LinkList example with the add method. That is the only way to manipulate multiple fields as a single atomic unit. You have to create a lock, enter it above, manipulate everything, release the lock when you're done. Was that? Okay, so I'm all caught up on the questions. All right, let's move on, because I think I'm running out of time. Now, I recommend avoiding the volatile keyword. Some of this I've said already, the reasons why. First is calling thread volatile read and thread volatile write explicitly in your source code is a huge red flag, and that's a good red flag. You want to see that because it makes you very cautious about how you can edit the code, reorder the code inside that method. Another thing about why not to make everything volatile is because making all access volatile hurts performance too significantly. So let me show you an example here. Let's say I had this line of code, mamount equals mamount plus mamount. Now clearly what I'm trying to do is I'm trying to double the value that's in mamount, right? And let's say mamount is a 32-bit integer. So I'm sure a lot of you know, what is the most efficient way of doubling a 32-bit integer? Right? Just think for a moment. Do you know what it is? Right? The most efficient way of doubling a 32-bit integer is just to do a bit shift, shift one bit left. Right? That is the fastest way of doubling a 32-bit integer. But if you mark mamount as a volatile field, then this first read is a volatile read of mamount, followed by another volatile read of mamount. Then the result of the two volatile reads get added together, and then a volatile write into mamount occurs next. So this one line of code is a volatile read, and now it has to be an add. Now it can't be a left shift anymore, so it has to be an add, and then a volatile write into mamount. So the code is a good bit bigger, and it's going to be a good bit slower to do all of this. Also, volatile field is not volatile if passed by reference. So here I'm calling int32 try parse method, and it takes in here a field as an out parameter, or ref parameter would be the same thing. And I'm trying to pass into it a volatile field here. And when you do that, the compiler issues a warning. Note it's a warning, not an error. So the code will compile, but it's giving you a warning saying this code may not work as you expect it to. And basically the warning is a reference to a volatile field will not be treated as volatile while it's inside that method. One other thing about volatile is that it's not common language specification compliant. And so if you have a public volatile field that might be manipulated by code in another language, for example, Visual Basic does not support a volatile keyword. So if you write a class in C# with a public volatile keyword and then somebody wants to consume that from VB, the VB code will not treat the field as volatile. You lose that too. So there's several reasons why volatile is really kind of the keyword is a bad thing. Calling thread volatile read and volatile write is good. And it's very fast, by the way. Volatile reads and writes are the fastest thing you can do that is thread synchronization related. There is nothing else thread synchronization that comes close to the performance of thread volatile read and write. And the reason is because, as I said before, these are special methods that the compiler turns into special CPU instructions. And the CPU instructions execute these things in hardware, which makes them blazingly fast. Right? You can't do anything faster. Herb Sutter says something. Let me make my window bigger. Whoa, that's a big question. Herb Sutter, in one of his mails, said, quote, volatile keyword in C++ is for hardware access, primarily memory mapped I/O, and was never meant to have anything to do with inter-thread communication. Unfortunately, it was mistakenly loaded with overloading guarantee semantics, and this was blah, 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 blah. Good thing is that the enormous semantics should be turned off by now. To which my question is the intended volatile semantics different in C# versus C++? Yes. So what I am describing is the intended semantics for C#. As I said a couple slides back here, right over here, so originally volatile in C++ meant that this first thing, the data cannot be cached in a register or in a temporary variable. And when you call a volatile read and volatile write in C# or .NET, that does the same thing. But volatile write and read in C# or .NET also does this program loitering semantics. So we have that in addition to the data caching. By the way, I also mentioned here that in native C and C++, there are these other methods, like there's this method underbar read-write barrier. So you might want to go and look that up, like do a Google search or a Bing search for underbar read-write barrier, and that is the native C, C++ equivalent of these methods over here. In .NET, we do not have an equivalent of what the original C volatile was for, because in .NET you never have direct access to hardware. Okay. All right, so now, there's some other questions. Let's do that, and then we'll do interlocked, and we're getting close to the end. So if it's so bad, why have the volatile keyword? It should not have been there at first. When do we use it? Can you give a scenario? Well, okay, so, some things, we have some bad things because at the time when they're created, we don't realize how bad they are, and then over time, we realize that they're bad. And then you can do things like remove them, but then that can break existing people's code. So what happened was the C# team at Microsoft, they thought Volatile would be really nice, and so they added it to the language. Then, at the C# Standardization Committee, which I was actually on that for a little while, there were people on the Standardization Committee who said this was really a bad thing and it should be pulled out, and they gave their arguments. But unfortunately, people on the C# team at Microsoft had already added it to the language, and so since it was added, some people used it, and then taking it out would have broken existing code. But by the time the Visual Basic team at that time had not added Volatile to the language yet, to their language, and then once they realized why Volatile was bad, the Visual Basic team said, well, great, we never added it, and so we never will. And so that's why Visual Basic doesn't have Volatile, and that's why C# does have it. It's really because of history, and we didn't realize how bad it was until people started using it, and then the problems, but then we don't want to break existing code. So, there's a lot of things that are like that in .NET. Well, in all platforms. This is certainly not a Microsoft-specific issue. Okay, let me take a sip of some soda here. Okay, and let's talk about the next thing, which is interlocked. Oh, when is the end of the session? I forget. Is it 11:30 my time, 12 o'clock? I only have 15 minutes left. Is that about right?
That's correct, yes.
Yeah, that's correct. Okay, so I don't have a lot of time because there are a lot of really good questions, and it was really good to get to those. So I'm going to have to move through this rather quickly at this point, and I just won't be able to get through all of it, I'm sure. So the next thing beyond Volatile, Volatile is the fastest thread synchronization thing you have at your disposal. Right? Clearly, if you're interested in high performance, avoiding thread synchronization is the best thing. If you can't avoid it, then you should look for the Volatile methods. They're your next fastest thing. If they're not good enough for you, then you would look to the interlocked functions. The interlocked functions are also special functions. And when the compilers compile calls to the interlocked functions, those calls also get turned into special CPU instructions as well. So that makes these things very, very fast, but they're not as fast as the Volatile functions. Volatile functions do either a volatile read or a volatile write. The interlocked functions, on the other hand, each interlocked function does both a volatile read and a volatile write. So they're really twice as slow because they're doing both a read and a write operation, but as a atomic thread-safe thing. So let's take a look at interlocked increment, the first method. Here we pass in a int32 by reference as its only argument. And what this method does is it reads the int32 value, increments it by 1, and then it volatile writes it back into the location. So you see it's doing a volatile read, add 1, and then a volatile write, but it does it as a single atomic operation. Okay? Like if you just said x plus plus somewhere because you want to add 1 to the variable x, that could be multiple CPU instructions. That could be read x, add 1 to it, then write it back out. That's 3 instructions, and the CPU could be preempted in between any one of those 3 instructions. But with an interlocked increment, that is a single CPU instruction that gets the value, adds 1, and puts it back in. And it cannot be preempted in the middle of that operation. That increment happens as a single atomic unit. That is what's so powerful and what is so special about this. And because it's done in hardware, that makes it very fast. We also have interlocked decrement, which, of course, reads the Int32, subtracts 1, and writes it back out. And we have, introduced in .NET 2.0, was interlocked add, where now you have the ability to read a value, add an arbitrary value. So now you can add 1, like increment does, or you could add 2, or add 3, or add 4, whatever, and then writes that back, the result back into location. And of course, for value, if you put a negative number there, then you're doing subtraction. So if you said add location -1, that's the same thing as calling decrement. So then you might say, well, why do we have increment and decrement if add is really a superset of that functionality? And the reason is because increment and decrement were introduced in .NET 1.0, add was introduced in .NET 2.0, and we don't want to break anybody's code, so we can't remove increment and decrement out of the platform. We just add new stuff in. Then we have interlocked exchange. What interlocked exchange does is it reads the value in location, then it writes value into location, and what's interesting about it is that it returns the value that it saw, okay, the value that it read. So I put above each of these methods in a comment what logically each of the methods is doing for you. But again, if you wrote that code above that I have in the comment, that's 3 separate statements that cannot be executed as a single atomic unit. These special functions perform the equivalent of those statements, but as a single atomic unit. And then, I don't know if any of you have a favorite function of all time, or in the whole world, but I do. And my favorite function of all the functions available to me in the whole world is interlocked compare exchange. With interlock compare exchange, this function is actually a superset of all the other functions. I don't need increment, decrement, or add, or exchange. I could do all of those things with compare exchange. And the way compare exchange is phenomenally powerful, and really when you're using compare exchange, you are using an optimistic concurrency pattern. So if you're familiar with optimistic concurrency patterns, that's what compare exchange is all about. Compare exchange is all about saying, let me look at what's in location. Is what I see in there, is that the same thing as this in comparand, what was passed here? Does it have the same value? If it does not have the same value, then do nothing and ignore this argument entirely. If, on the other hand, when you call compare exchange, if the value in location is equal to the value in comparand, then it will do the exchange, which is put value into location, which is the same thing as what exchange does up above. It puts value into location. And then compare exchange, it returns the old value. That is what it saw in location at the time when you called it. The other thing I'll mention is that each of these interlock functions, because they're both a volatile, they're equivalent of a volatile read and a volatile write, each one is a full memory offense, which means that when you call, let's say, increment, just to pick one as an example, any code you have above it must execute to completion before this thing is executed. And any code you have below it must happen below it. Right? So just like we talked about volatile write before, any lines of code you have above must run to completion before the write occurs. And we talked before about volatile read, that after a volatile, any code you have after a read must be read after the read. Well, the same is true for all these interlocked APIs. They are the equivalent of a read and a volatile write operation. So any code you have above must execute above. Any code you have below must execute below. By the way, all locks internally use the interlock functions. So monitor enter internally calls an interlocked API. Monitor exit internally calls an interlocked API. Same is true with reader writer lock slim, reader writer lock. Same is true with the kernel objects like mutexes, semaphores, events. All locks internally will use interlocked APIs. That means that all methods on a lock are a full memory fence. So any code you have above acquiring a lock, that code must execute. In fact, here, I'll go back to the very first slide. Right, the LinkList example. In the list link example, here I'm acquiring a lock. Well, that a call to acquire is a full fence. So any code that I had above acquire, that must execute to completion before acquire is called. Any code release is a full fence too. So any code in between acquire and release, that code is guaranteed to execute within acquire and release. And any code I have after release, that code is guaranteed to execute after the call to release. So by putting these calls to enter and leave locks in here, those internally call interlocked APIs. Interlocked APIs are full fences, memory fences, and that's guaranteeing or turning off optimizations from the compilers and CPU to ensure that code you have outside the lock is outside the lock. Code you have within the lock remains within the lock. Right? You kind of are getting that for free, which is very nice. We like that feature. All right, let me go back to where I was. So that's the interlocked APIs. Now, I know I'm allowed to go over time a little bit, and I think I'm going to take advantage of that. So let me show you an example of using these interlocked APIs to show you how powerful they are. What I show on this slide here is a very common problem that a lot of people need to solve. And the most high-performance, efficient way of solving this problem is by using the interlocked APIs. So first, let me explain to you the problem. I have an application, and in my application, I want to make a request out to many, many, many websites, or database requests, or web services. Doesn't matter what it is. And after all of those requests have come back, I've got the responses to all those requests have come back, I now want to do some processing to munge those results together and then show some kind of aggregate result back to the end user. I want to do that using as few threads as possible, so using as little system resources as possible. I want it to run as fast as possible. I want my program to scale. So if I'm running on a machine with a single CPU, I want to use only one thread to do all the work. If I'm running on a machine with 4 CPUs, then I want to use 4 threads to do all the work. So based on the hardware I'm on, I want to use the hardware that's available to me. I also want to give the user the ability to cancel. So if it's taking too much time for the results to come back, and the user says, you know what, I don't want to wait anymore, I want to cancel it, I want to give them that ability. I also want to specify a timeout myself. So in my code, I'm saying, well, I'm only going to allow 5 seconds for this to happen. And if it's taking more than 5 seconds, then I want to simulate that the user is canceling the operation. And I'm just going to say, look, user, here's what I got back in 5 seconds worth of time. I'm not going to wait for everything else to come back. Okay, so that is a very common problem, actually, that many people have. Multiple requests, wait for the results, support timeout, support cancellation, don't block any threads, use system resources efficiently, and so on. Let me show you how I'm going to use the interlocked APIs in order to solve this problem. In this code here, I have a class called multi-web request. And inside here, I knew up an async coordinator. Now, this is the class that actually does all of the coordination of the asynchronous operations. And the code for that is on the next slide, and I will walk you through it. Then that's the code that has the calls to the interlocked APIs in it. Then, when this object is constructed, I knew up an array of web requests. So in my example, I'm going to make a bunch of web requests to Wintellect.com and DevScovery.com. And here I'm only making a request to 2 websites, but this code would actually work for up to 2 billion websites, because the interlocked APIs work on a 32-bit integer, and a 32-bit integer can be up to 2 billion. Right? You can express the number 2 billion in there. So I'm only using 2, but this code scales phenomenally well to very large numbers, very efficiently. Because I'm going to be making 2 requests, I expect to get back 2 web responses. So I create an array of web responses that can hold 2 responses in it. Here's the code for the constructor. In the constructor, I have a for loop that's going to walk through each of the requests, and just before I initiate a request, I call on the async coordinator about to begin one request. So that tells the async coordinator I'm about to begin a request. Then I call begin get response. Now here I'm using the .NET Framework's asynchronous programming model, which is a way to initiate I/O operations asynchronously without blocking any threads, which I love it. It is awesome. Of course, in .NET 4.5, they have a slightly different version of this, which I actually do have a slide on to show you, if you were using .NET 4.5, what the equivalent of this code would look like. I'll get to that later on. But here I'm using the .NET 4.0 and earlier versions of what this code would look like. So here I'm saying for a particular request, let's go and get it asynchronously, and when the response comes in, I want a thread pool thread to call this method and get response. And then I loop this around. So basically I'm saying Wintellect.com, give me your data. Discovery.com, give me your data. And my thread doesn't block for any of this. After I've initiated the 2 requests, I call all begun. And this says to the async coordinator, when I've finished initiating all my requests, and when they're all done, please go and call this method all done, which is a method I have down here below. And then, of course, in here, you would write the code to go and process all the responses. And this method will only be called back when all the responses have come back in from all the web requests I've made. And actually, that's not completely true, because you're passing a status here. And there's 2 other reasons, or statuses, why this method could be called. You'll notice that when I call all begun, I also get to pass in here a number. I'm passing in 5,000 milliseconds. So this says, after I've made all the requests, and if they don't all come back in 5 seconds, then I want all done called, and it'll be passed in here a status of timeout. So our program will be told that we didn't get all the responses back within the 5-second period of time. There's another status too, by the way, which is cancel. And I'll show you on the next slide how the user can cancel this. If the user doesn't even want to wait the 5 seconds, maybe they only wait 3 seconds, they say, I've had enough of it. But while we're on this slide, let's look at what happens when the websites return their responses. As the website returns the responses, various thread pool threads will call this method endGetResponse. And I could actually have multiple thread pool threads calling into here simultaneously if I'm running on a machine with multiple CPUs. So this means my code will scale beautifully depending or based on the hardware I'm actually running on. Inside endGetResponse, I go and I get the results from that web request, and I store it in the proper location of the response array. And then I tell the async coordinator that one of the requests has just responded. And then, so now the async coordinator knows as responses are coming back, when they all come back is when it knows to go and call all done. All right, so that's the basic code here, and you could write, your code here and just reuse this async coordinator class as a reusable component in order to get the desired behavior. Now, let's talk about the async coordinator class, and I'm going to show how it works internally. Well, first, it has a field in here called m_ops, which I initialized to 1. This is the most important field of the whole class, and it is a counter that represents the number of operations that are outstanding. On the previous slide, just before I initiated an asynchronous request, I called this method about to begin. And I always passed in here the number 1. And all I do in here is I call interlocked add to, in a thread-safe atomic way, add 1 to m_ops. So every time I'm about to initiate a request, I just add 1 to the number of operations. Now, when the for loop was done on the previous slide here, I then called all begun. So let's look at what that does. And all begun, I pass in here a callback method, which I simply save in a field, and then I pass in a timeout value in milliseconds. So here I new up a timer, a .NET threading timer. And then I say I want this timer to go off in 5 seconds. And when it goes off, it should call this method time expired, which is a private method that I have declared down below. Then I internally call just ended. Just ended is this method right over here, and let's see what it does. Here you'll notice I call interlocked decrement. So this means subtract 1 from m underbar ops. Now, interlocked decrement, it returns what the calling thread has done to it. And I compare that with 0. So what this if statement is really saying here is, did this thread set m underbar ops to 0? Well, if it did, that means we're done all our operations, and therefore we want to call the callback method. But if this thread has not set the count to 0, that means there are still I/O operations that haven't completed yet. And in that case, we will not call invoke, and we will just return from just ended back to all begun, and from all begun back to the constructor over here, and then from the constructor back to whatever code called us. Now, in the future, these I/O operations will be completing. And these thread pool threads will be calling into this method, and we can have multiple threads calling into here simultaneously, remember. That means multiple threads could be calling into just ended simultaneously. And as they do that, multiple threads will be calling decrement simultaneously. But decrement is a thread-safe atomic operation. That's the beauty of this function. And so one thread will decrement the count from 2 to 1, one thread will decrement it from 1 to 0, and then eventually one of those threads will say, oh look, I'm the one who processed the last response. And because I'm the thread that got the last response, it's my responsibility to call the callback method and tell it we're all done, we have all the responses in, go and process the responses. So that brings us to invoke. Let's talk about invoke. As I mentioned, there are 3 reasons why invoke could be called. It can either happen because all the I/O operations complete, or our timer, which we set to go off in 5 seconds, if a thread pool thread could call time expired, and then we'll call invoke with a status of timeout. Or this is a public method here called cancel, which means we could put a cancel button in our user interface, and when the user presses the cancel button, we could go and call this cancel method, which also calls invoke with a status of cancel. And it is possible that 3 different threads could be calling these 3 methods at the exact same moment in time on 3 different CPUs. So now I have a race condition, and I need to arbitrate the race. I need to pick 1 thread to be the winner, and I need to pick 2 threads to then be losers. So let me show you how I do that. I have created another field up here called m underbar invoked, which I really treat like a Boolean variable. So 0 means false, and that's what it's initialized to, and 1 would mean true. So now 3 different threads could all be calling invoke over here at the exact same moment in time. And I call interlock exchange. And interlock exchange says, let me read the value of invoked and let me set it to 1 as a single atomic operation. And the exchange returns what it saw when it did this. So what this line of code is really saying here is, am I the thread that saw 0? If I'm the thread that saw 0, that means I'm the first thread here. No thread has beaten me here. I'm the first thread to get here. Therefore, it is my responsibility to call the callback method and pass in the desired status. If a second thread gets here, it will read a 1 and change this to a 1. But that will not be 0. So since it read a 1, the second thread is saying, oh, some other thread got them here first. So some other thread is calling the callback. I should not do that, and therefore it's a loser, and it doesn't call the callback method. And of course, any future thread that shows up here is also going to see a 1. It's going to say, oh, some other thread got here first. It's not me. So that means the callback's already being called, so I should not call it. And that's how I solve the race. No threads are blocked in the making of this program at all. It scales phenomenally well with very high performance using very little system resources and solves what really many people have as a very common problem. Okay, are there any new questions that anyone would like to ask? After the user cancels, do the responses from the interface still call their completion callback? Yes, they do. So after cancel is called, or if timeout happens, then the I/O responses are still coming in from the websites, and the thread pool threads will still be calling, will still be calling just ended over here. And just ended will still be decrementing this count to 0. And when the last one comes in, we will hit 0, and then we will call invoke, but this will say cancel or timeout has already occurred, and so your callback does not get called. So basically everything will just get thrown away. So the responses do come in, but everything just gets thrown away. Good question. Are there any other questions? Can I show an example of how to use interlock compare exchange to do the work of add? Unfortunately, the code's not trivial, is the problem with that. And I do have a slide on it, which I normally do show, but I didn't think I would have time to show it, so I took it out of the slide deck. And yes, I did. I took it out of the slide deck. However, in my book, and I know I have magazine articles on it too, I do show this interlock any pattern. And in that pattern, I walk through the pattern and I explain how you can use interlocked compare exchange to do all kinds of things, like add minimum, an interlock minimum, an interlock maximum, an interlock bit test and set, an interlock set, a bit clear, a bit set, all those kinds of things. Anything basically you could do with an integer, an interlock multiply, interlock divide. I show how you can accomplish all of those things. But I don't have time here today to do that. Very briefly, if you are using .NET 4.5, this is the equivalent. So it's the same async coordinator class. That class hasn't changed at all. But now I use the HTTP client class, which is new in .NET 4.5, and it is the preferred way of making HTTP requests. And then I now say get byte array async. So instead of calling begin get response, I call this get byte array async, and then I say continue with, and then I say compute result over here. Most of this code you'll notice is identical to what we had before. Compute result is the callback method that gets invoked when the I/O operation is complete. Inside here, there's a little bit of stuff about if there was an exception or how to get the result out, save it into the result array, and then call just ended, and then the all done method would be exactly the same as what you had in the previous example. So I just put this up here mostly for reference in case you're using .NET 4.5. The async coordinator code is exactly the same, the model's exactly the same, but a couple of functions are slightly different. Okay, the last thing I would normally show you here is how you could build a spin lock, but due to time constraints, I'm just going to skip over this, but it is showing a use of interlocked exchange over here, as well as a use of thread volatile right to how to implement a spin lock. This spin lock would be the best lock to use for my LinkList example at the beginning. Spin locks are, remember I said that if you have multiple operations that you need to perform as a single atomic unit, you must use a lock, and you must acquire the lock or enter the lock and leave the lock when you're done. A spin lock is the highest performance lock there is. And this is basically how a spin lock is implemented internally. It uses interlocked exchange, and it uses a volatile right in the leave call. And in .NET 4, or starting with .NET 4, there is a system threading spin lock class that is largely implemented internally, just like what I show here. And this would be the best lock you could use in that LinkList example, because you know it's just 2 assignments that's happening there, and that's very fast, very few operations, and I want the highest performance thread synchronization possible on that. A spin lock would be the best choice. All right, and with that, I've finished the slide deck. I'll take a few more questions, and then we'll be done. But again, you feel free to email me if you have anything else. So one new question here, is the task parallel library the best way to use async programming in .NET 4.0? Is async CT ready to be used in .NET 4.0? Okay, so the task parallel library stuff, which was introduced in .NET 4.0, what that is all about is compute operations, not about I/O operations. So the task parallel library is useful when you have lots of computation and you want to distribute that across the CPUs that you have in the machine. It is not for, I want to make a request to a website and to a database and to something else all simultaneously. That is the task parallel library is an extremely inefficient way of doing that. The asynchronous programming model is the correct way, or the efficient way, of making multiple I/O operations execute in parallel. So I want to be really clear about that, okay, because it's very misunderstood, and people use the task parallel library for doing I/O operations concurrently, and that is very, very inefficient way of doing that. So is it the best way of doing async programming? I don't know exactly what you mean by async programming. If you mean, is it the best way to concurrently execute computation? Yes. Do you mean, is it the best way of doing I/O operations? Then the answer is no. Now, of course, in .NET 4.5, they've introduced this new async and await keywords and the stuff I was just showing, and that allows you to use tasks in order to do I/O operations in an efficient way. So that's good stuff. Which, by the way, I worked on that stuff at Microsoft to produce it. Okay, the interlock compare exchange was too hard. User cancel, I answered that. Is there a possibility that interlock decrement could execute, but the thread could interrupt before the compare to 0? Yes. Good question. That is possible, but it doesn't matter. And the reason is because integers are value types. And so when you call any interlock function, increment, decrement, doesn't matter, all of them, they return this integer back to you, and that integer returns back to you what the calling thread did to it, and then you are comparing that return value with 0. So it doesn't matter what's inside the global or field integer anymore, because you are getting back a copy, right, the value type integer of what was there. So yes, your question's a great one. Yes, that is possible, but it doesn't matter because of the way the code is written, and that's great. Your generic method morph is a diamond. You need to do one more talk to get all the topics in your serial. Well, thank you very much. And what he's talking about is in my power threading library that I make freely available on the Wintellect website. I have a interlocked morph method which wraps all of the behavior of interlock compare exchange that allows you to pass a callback method in that refers to some piece of code that's not thread safe, which is morphing an object in a not thread safe way, but my morph method uses compare exchange internally in order to make it become thread safe. And that's really the reason why compare exchange is my favorite function. With interlock compare exchange, I can take some operation that is not thread safe, and I can make it become thread safe in a very efficient, high performance way without blocking any threads. And yes, maybe I'll do another talk on LIDNUG sometime in the future, and I can go into so much more about this. I love this stuff. It's just it's so much fun for me. I really love it. Okay, we really are running out of time, but I can answer maybe a few more before we go. I have some file access code that I had heard. It's running on Windows Phone. 2 threads could try and access different parts of the file at the same time. I'm rewriting the code so that seek and read are in the same function, and then I can put a lock around those 2 lines, e.g. stream, lock, seek, stream. Is there a more efficient way to do that? Well, first of all, I don't like the lock keyword in C#, so I would strongly discourage you from using that. I would instead recommend that you explicitly call monitor enter and monitor exit around the code. And then the answer to your question is no, what you are doing is the most efficient way of solving that problem. I think you're trying to talk to me. Are you trying to tell me, Brian, that I'm going over by too much? Let's see. going to have to cut it short now. All right, people are leaving us slowly. All right, so I can take some more of these questions in email if you want to email them to me, but people are leaving, and I'm already over by about 20 minutes. But I had a great time. I really enjoyed this topic a lot. So I hope you've enjoyed it too. If you do have any more questions, please just email me, and I'll be happy to do it that way. I'd rather not do it by chat. All right, thank you, and goodbye, everybody.
Fantastic. Thank you, everybody. Quickly just want to announce the winner of the Wintellect virtual training session. The winner is Dan Vestergaard, and congratulations, Dan. I've already given Dan the details to contact Bethany, and Bethany has been informed about it as well. So thank you very much, everybody, and we definitely hope to see you again, Jeffrey. Very exciting and interesting topic. Looking at the questions that kept coming in and are still coming in, I think it's obvious that we're going to have to beg you to come back again.
Yeah, I think we're going to have a round 2 on this one, Brian. Absolutely, for sure, yes, mate.
Definitely.
Well, what say you, Jeffrey? You're up for a round 2?
Yeah, absolutely. I love this stuff so much. It's so much fun for me. I don't realize how much carried away I get.
Well, we all do the same. I have a strong feeling that I'm going to have the same problem tomorrow night.
I'm stopping the recording.
Yep. 3, 2, 1, down.